You know, when you think of an atomic bomb, you imagine it detonating over a city. But what if one exploded silently, almost 100 kilometers up in the sky? Well, that's not science fiction. It's exactly what happened in May of 2023. Let's get into this absolutely incredible cosmic event.
Okay, so this is where it all started. May 25th, 2023. An all-sky camera down in Brazil caught this, just this breathtaking image. You see that brilliant streak of light? And then that massive flare at the end? Yeah, that wasn't just some pretty shooting star. That was an explosion with the power of a nuclear weapon.
So later on, scientists went back and did the math. They calculated the sheer energy that this thing released. And the number they came up with? It was just staggering. 21 kilotons of TNT equivalent. Now, to really put that number into perspective for you, the scientific paper that described this event makes a pretty chilling comparison. This was basically the same amount of energy as the atomic bomb dropped on Nagasaki. The only difference? It all went off in the quiet of the upper atmosphere.
So, what in the world was this thing? And how did scientists even begin to piece its story together? First, let's really wrap our heads around the sheer scale of what they were looking at. Yeah, according to the researchers, this wasn't just some big meteor, no. This was a straight-up record breaker. It was the single largest fireball ever documented in that entire region. The technical term for an event like this is a super-bolide. It's basically a meteor that's so incredibly bright that it violently breaks apart or just explodes when it hits the thicker layers of our atmosphere. And believe me, this one was definitely a super one. So, think about this. How do you investigate a crime scene that's 96 kilometers high and literally vanished in a matter of minutes? Well, you assemble a team of very specialized witnesses. And this is where the real scientific detective work begins.
On the left, you've got our first eyewitness, that all-sky camera that saw the flash. But now, look over at the right. A totally different instrument, something called a LIDAR. It detected something else entirely. It saw this weird chemical trace, a sudden cloud of sodium and potassium atoms just appearing in the sky. These were the first two major clues.
Now, the next piece of the puzzle came with some unbelievable precision. There's a meteor radar system that normally tracks tiny little meteor trails, and it picked up this absolutely massive echo. This lets scientists pinpoint the exact time of the explosion down to the millisecond, and they pegged its altitude at 96.2 kilometers up.
Then came another clue, but this one was electrical. An instrument called a digisonde, which keeps an eye on the ionosphere, detected this sudden, really dense patch of electrons. They call it a sporadic E layer, popping up right after the event. So this bolide hadn't just left behind a chemical signature, it had actually electrically charged the atmosphere.
All right, so our detectives have their clues. A flash of light, a mysterious chemical cloud, a precise radar echo, and a weird electrical disturbance. The big challenge now is making it all fit together into one single coherent story.
But right away, there was a huge problem with the evidence. You see, the LIDAR that spotted that chemical cloud, it was nearly 200 kilometers away from where the explosion actually happened. So how on earth could that material have traveled so far, so incredibly fast?
The answer, it turns out, was hidden in another piece of data. That meteor radar wasn't just a timekeeper. It also measures high-altitude winds. And the data revealed these powerful winds just ripping along at up to 75 meters per second. It was like a cosmic conveyor belt that just scooped up the metallic dust from the blast and carried it right over the LIDAR sensor. Mystery solved.
So how did they get to that incredible 21 kiloton number? Well, the process is actually fascinating. The explosion created this powerful but totally silent sound wave called infrasound. Just under 5 minutes later, GNSS satellites actually detected this wave as a ripple passing through the ionosphere. By measuring the wave's period, scientists could plug it into a special formula, one originally developed for nuclear explosions, to calculate the blast's true power.
But you know, this story isn't just about a really cool, spectacular explosion in the sky. It actually has a surprising and very modern consequence. It's kind of a warning shot for all the technology we have up in orbit.
And that's because the shockwave from this super-bolide, it didn't just stop in the atmosphere. No, its effects kept going, propagating hundreds of kilometers higher, reaching all the way into space itself.
So let's bring in our final witness. 4.5 hours after that initial explosion, the European Space Agency's Swarm B satellite happened to be passing by the area, and it measured something pretty unexpected.
At an altitude of 530 kilometers, I mean, that's well into what we consider space, the satellite measured a 15% spike in the atmospheric density. The air up there, as incredibly thin as it is, had all of a sudden gotten thicker. The energy from that explosion had literally puffed up the very top of our atmosphere.
Okay, so why does this matter? Well, for a satellite, flying through thicker air is kind of like you trying to drive your car into a really strong headwind. It seriously increases atmospheric drag. And this unpredictable drag can push a satellite off course, and over time, it'll cause its orbit to decay much, much faster.
So the takeaways here are really, really important. This extra drag means satellites have to burn more precious fuel just to stay in their proper orbits, and that shortens their operational lifespan. But maybe the scariest part is that unlike solar storms, which we can sort of predict, these super-bolide events are completely random. They're almost impossible to forecast.
And all of that leaves us with a really critical question. We spend a lot of time and energy worrying about threats from space, like asteroids hitting the Earth, but what this event shows us is that even meteors that burn up high above our heads can have very real consequences for our technology in orbit. As we become more and more reliant on that vital satellite infrastructure, we have to ask ourselves, how do we protect it from the sky itself?